When we think of climate change, it's easy to obsess about what's happening now and in our recent past. This week is about getting a perspective on climate change and realising that the Earth's climate has self-regulated for the past 4.5 billion years. And the Earth has been a habitable place for life for almost all of that time. Explaining climate change over 4.5 billion years of Earth history is a complex puzzle. There are so many pieces, and they're not simple two-dimensional pieces. They're complex objects that interact together, forming feedback loops that lead to emergent behaviour. In fact, there are two puzzles that we need to solve. The first of these puzzles is related to the engine of our climate, the Sun. The solar system was born 4.5 billion years ago. At that time, our Sun was 25 to 30% less bright than it is today. If we took today's blanket of gases that surround our planet and turned the Sun down by 25 to 30%, the Earth would be around 20 degrees centigrade colder. In other words, the early Earth would have been frozen. But here's the puzzle: it wasn't. Evidence shows the Earth was covered in liquid water since around 4.2 billion years ago, and there's been life on the planet, which needs liquid water, since as far back as 3.8 billion years ago. Also, there is even more puzzling evidence that the early Earth was actually warmer than it is today. How can we explain this? We have evidence to suggest that there was a thicker blanket of warming gases in the atmosphere, particularly carbon dioxide and water vapour, at a time when the Sun was fainter than today. So, despite the Sun being fainter, this thicker blanket of warming gases kept the Earth warm. But hang on a minute, if there was much more carbon dioxide in the atmosphere back then, where did it all go? After all, today carbon dioxide makes up only a tiny part of our atmosphere. The answer is underneath us, in sedimentary rocks to be precise. As the continents developed, they weathered. The key process here is chemical weathering, where carbon dioxide in rainwater forms a weak acid, carbonic acid, that dissolves silicate rocks. The carbon, in the form of bicarbonate ions, washes into the ocean, where it is used by many organisms to form their shells, which are then deposited on the ocean bed to form carbonate rocks. In short, carbon dioxide from the atmosphere is transferred through the hydrosphere to be stored in the lithosphere. This explains how our climate has self-regulated. Even though the Sun is getting brighter, we haven't seen a proportional increase in the Earth's temperature. This is a classic example of negative feedback. As the Earth's temperature began to increase, then so did the rate of chemical weathering. The increased rate of weathering in turn succeeded in storing more carbon in the rocks, so reducing the atmospheric levels of carbon dioxide and thinning the warming blanket around the Earth, counteracting the increase in temperature. Without this negative feedback, as the Sun got brighter, the temperature today would have risen much higher than we are currently experiencing. Okay, that explains the first puzzle, but there is a second one. 2.2 billion and again 700 million years ago were two periods in Earth history that were extremely unusual. Our planet became a giant snowball. How did snowball Earth come about, and why, ultimately, did it melt? This is an example of how feedbacks can destabilize as well as stabilize our climate system. If something acts to cool the planet, like the growth of continents increasing the removal of carbon dioxide by weathering, then ice cover on the planet increases. But as ice cover increases, reflectivity from the surface also increases. This reflectivity reduces the absorption of sunlight by the Earth's surface, and so decreases the temperature further, which increases ice cover, and so on. This produces a positive feedback that we met in week 1. Usually this feedback is constrained. It amplifies the spread of ice cover away from the poles, but then the climate system restabilizes. However, if cooling is sufficient for ice cover to reach around 30 degrees of latitude, the tropics, a tipping point is reached, a point where the process of amplification of ice cover runs away. Then we get a snowball Earth, with the ice closing up at the equator. So what has stopped this feedback mechanism encasing us permanently in ice? The answer, again, lies in the carbon cycle. Remember the chemical weathering process? Well, if we cover the Earth in ice, we stop the process of weathering. However, we still have volcanoes pumping out carbon dioxide into the atmosphere. Because the sink of carbon dioxide has been switched off, the carbon dioxide from volcanic activity builds up and up and up in the atmosphere, and this thickening, warming blanket begins to melt the ice at the equator. Once this happens, the same feedback mechanism kicks in, but working in the opposite direction. The exposed ocean, a dark ocean surface, absorbs the sun's energy, melting more ice, and the feedback runs away in the opposite direction, melting all the ice. With the high carbon dioxide levels as well, we get a superheated world with no ice caps. It's a bit like coming out of the freezer and into the frying pan. Of course, what happens then is that the weathering process, which was shut off by the ice cover, now acts on all the carbon that's in the atmosphere, returning it to the Earth's crust. Our planet's climate has key instabilities that can cause it to turn into a giant snowball or to overheat. In the past, the climate has lurched from one extreme to the other at least twice. And there have also been less extreme switches between hot and cold periods, our last ice age being a good example. Could climate change be any worse? Out of the freezer and into the frying pan sounds as bad as it gets, right? Well, not really. There is actually the possibility to go from the freezer straight into the fire. Our sun is getting steadily brighter, but luckily for us, this happens very slowly. At the moment, we're orbiting the sun in what we call a habitable zone, a zone where water occurs as a liquid that can support life. Our near neighbours in the solar system, Mars and Venus, are both just outside this habitable zone. Mars is on the freezer side, Venus is on the frying pan side. Well, actually it's the fire side, because the surface temperatures on Venus are hot enough to melt lead. As the sun gets brighter, the habitable zone moves outwards, and we get closer and closer to this hot inner boundary. Let's gaze into the future for a moment and think what will happen to our climate as the sun continues to burn brighter. As temperatures rise, the atmosphere begins to fill up with water vapour. Eventually, levels of water vapour reach such a high level that they become super efficient at trapping the heat radiation coming off the Earth. Most of the outgoing heat radiation is sent back to the surface by the increasing volumes of water vapour. The atmosphere becomes quite literally like a pressure cooker. The Earth loses its energy balance and simply cannot shed heat as quickly as it is coming in from the sun. In the end, the oceans evaporate and the conditions that support life are lost. The death of the biosphere. Our planet's climate has changed thanks to natural forcing factors throughout its history. A steadily brightening sun and two key feedback mechanisms have seen the climate lurch from relatively warm to colder conditions.